Good morning. Welcome to the plenary session of the 2026 USNC-URSI National Radio Science Meeting. I am Jamesina Simpson. I'm the chair of USNC-URSI, and I'd like to welcome you to our new location, the Limelight Boulder Hotel. For 51 years, we were on the University of Colorado campus, just next door, but this year they decided to move their semester a week earlier. So this gives us the opportunity to try out this new hotel in Boulder. Since this is a slightly different part of Boulder that we're in, as you're looking for places to eat and get coffee, we've listed a few places on our website. I'd like to take a moment to thank all of our sponsors for the 2026 National Radio Science Meeting. We have 2 gold sponsors this year, Johns Hopkins Applied Physics Laboratory and the IEEE Geoscience and Remote Sensing Society. We also have bronze sponsors, MITRE, the Department of Electrical and Computer Engineering at the University of Utah, and the Department of Electrical and Computer and Energy Engineering at CU Boulder. URSI is a continual sponsor of our Women in Radio Science reception that will be held on Thursday evening. And we also have a technical co-sponsor, IEEE Antennas and Propagation Society. So thank you to all of our sponsors. For those of you who are a little bit newer to our community, I have just a brief introduction to the International Union of Radio Science. It was begun in 1919, and it coordinates studies, research, applications, scientific exchange, and communications in all fields of radio science. We're divided up into 10 commissions, which are listed here, and encompassing all aspects of electromagnetics. Each member country of international URSI has a national committee. And so our national committee is the United States National Committee for URSI, for short, USNC-URSI. We are appointed by the National Academy of Sciences, Engineering, and Medicine. And you can check out our website for more information. We also have a presence on LinkedIn and YouTube where you can follow us. USNC-URSI has an important presence in the United States because we're the only organization in the US that represents applied electromagnetics. And the National Radio Science Meeting, which you're at right now, is one of the few conferences that fosters and promotes works in progress, which is one reason why we have the one-page abstract that you're able to submit. It also provides a nice opportunity to meet program managers who often attend this conference from DoD, National Science Foundation, and so forth. And we also make a big point of supporting students to attend this conference with travel support, a mentoring luncheon, which will be held right after the plenary session today, a student paper competition, and our friendly atmosphere. USNC-URSI is organized in trienniums, just like International URSI is. And this happens to be the last National Radio Science Meeting in the current triennium. And so just to look back in the last 3 years, or 2 at the moment, because we're finishing our 3rd, is that we were able to hold our first all in-person National Radio Science meetings after COVID. And we were also able to recover from the COVID time for the number of paper submissions going up from 286 up by 100, up to 380 that we have this year. We've also doubled the number of sponsors for the National Radio Science Meeting with 2 gold sponsors as well, doubled the number of workshops and short courses where we were able to hold yesterday, the day before this plenary session. We've created new websites for USNC-URSI and also for the National Radio Science Meeting. And we now created a presence on LinkedIn and YouTube, so I hope you will follow us there. And we started hosting e-lectures. There are 4 currently available that are recorded and available on the USNC-URSI website. And our 5th, which I'll have a slide for shortly, a little bit later, will be held in February. And then, which will be introduced here in a few minutes, we've created the United States Foundation for Radio Science. And so a number of people were involved in all of these activities, and I want to thank them for all of their contributions. And a look ahead at the next triennium, Dr. Christopher Anderson, who is seated here towards the front, will become the chair of USNC-URSI. And there's also going to be a group of new commission chairs and other people going into their new positions. And so I encourage all of you to go to the commission meetings that are being held this week, tonight at 5:15 and tomorrow at 5:25. You can see how the 10 commissions are divided up into different commission meetings. And so students are encouraged to attend, visitors are invited to attend. You don't have to be a member. You can learn more about what all the commissions are doing and USNC-URSI. And aside from commission chairs and these other positions I've mentioned so far, there's many other ways to get involved in URSI. We have other positions in members at large, for example, Women in Radio Science chapter. And for this meeting, we have one of our big efforts is to have lots of special sessions. And so we need special session organizers, and we need help with reviewing, chairing sessions, and getting sponsors and so forth. So I encourage you to look at our opportunities to get involved. And if you would like to become a member of one or more of the USNC-URSI commissions, there's currently no cost for that. It does require a vote by the current commission members, but there's a number of benefits, including reduced registration costs. You can get eligibility for holding leadership positions. We also send out emails for announcements throughout the year, and so you can keep up to date on what's going on in USNC-URSI. And I just mentioned that there's an early career opportunity for students who can also become members. And so yes, this is one thing I mentioned earlier is our 5th e-lecture will be on the 27th of February. It'll be offered by Professor George Eleftheriadis. And here are the links which you can find on the usnc-ursi.org website to previous lectures and on YouTube. And with that, I'd like to hand it over to Mike Newkirk, who will be introducing the United States Foundation for Radio Science.
Good morning, everyone. As James just said, I'm Michael Newkirk. I happen to be the immediate past chair of the current triennium, so in one more year, I will be no longer an officer of USNC. I will say this is one of my favorite places to be. I started coming here, joined the Commission F membership back in probably the 1990s, so I've been doing this for a little while, and I really enjoy this conference tremendously. It's very exciting to be in this new venue where we can all be in the same place, don't have to worry about snow that might be coming tomorrow, so this is a great place to be. So I wanted to introduce what's called the United States Foundation for Radio Science. This is something that we set up this past year. We established it as a nonprofit corporation in the state of Maryland, where I live, back in August, and its mission is to support U.S. engineers and scientists as they advance the state of the art in a wide range of areas relating to applied electromagnetics, from radio astronomy to wireless communications, radio frequency devices, antennas, propagation and remote sensing, and biomedical applications. It reads a lot like that list of 10 commissions that you saw just a moment ago. So the motivation was driven by something that happened in the early part of this past year. The National Science Foundation, as many know, experienced a lot of changes, and one of the things included discontinuing the funding for the National Academies of Sciences, Engineering, and Medicine, which was used to manage 18 different relationships with different international unions, including ours. The academies, for many, many years, has been managing what we call the private fund, and this is used to organize the meetings that are held here in Boulder for the past 50-some years, as well as co-sponsoring meetings, the summer ones with the IEEE APS Society, which we've been doing for many, many years, and of course supporting to attend these meetings as well as the URSI flagship meetings. So that is really the sole reason that we have that private fund. The issue now is that with no NSF funding, the academies can no longer manage that fund. So we established the nonprofit for the primary reason of continuing to support what we do here at this meeting and others for U.S. scientists and engineers. In the future, we'll continue to do this. We're happy to be in a new facility. We're learning some things, and we'll be looking for some feedback from you at the end of the conference. And we want to continue to offer the travel support for students, our guest speakers, including the two that you'll see during this session. We'll continue to support the URSI flagship meetings. You'll hear our URSI president. We are honored to have him present. He'll talk about that in a moment. And then we'll continue to support the IEEE APS URSI meetings, the ones that we have in the summer. And again, we have our president of APS here today to talk a little bit about that. There's also some joint meetings that we hold with other national committees. Most recently, we had one in Florence with the Italian committee. Every once in a while, we do this with the Canadian National Committee, and not this coming summer, but the one after, we'll go to Kyoto and partner with the Japanese National Committee. All of this, with regard to the AP meetings, requires a new, what we call a memorandum of understanding that explains how our different organizations interact, and we're currently in process of working on that. So with that, I just want to give you that brief introduction and then turn it back over. Thank you.
Thank you, Mike. So I'm excited to announce that we have both the president of URSI and the president of IEEE Antennas and Propagation Society here with us. So I wanted to give them a moment to say a few words to you. We have Ari Sivola, who traveled here from Finland, and also CJ Reddy, APS president.
This is you.
Yes. Thank you.
Thank you very much for this introduction. So, dear friends of radio science, ladies and gentlemen, during the past 35 years, I think I have been 5 times in the Boulder meeting attending this wonderful place, but this is my first time in this role as the president of URSI. And it is my great privilege and great pleasure to greet you on behalf of our international URSI, our URSI Central, as we say. As was mentioned already, so URSI is a very high-level organization, works under the auspices of International Council for Science, or International Science Council. More than 100 years ago, it was founded, and URSI, the radio science, was one of the founding unions of that time it was called International Research Council. It became ICSU, International Council of Scientific Unions, but now a couple of years ago we merged together with human sciences, social sciences, so that is a very big organization working under the United Nations. So we are responsible for stimulating and coordinating these radio science activities, and of course we have our meetings and our efforts to exchange scientific information. Well, this definition may sound a bit circular because it doesn't define what radio science is, but just wait a moment. So we have 44 member committees, like one of the very and most active ones is of course the USNC member. Sometimes people call national committees, but that doesn't necessarily mean a country, but member committee is then which has a vote in our council, which comes together in each General Assembly. So they are the members, but we also have the individual membership. As we heard also, the member committees may have individual memberships, the commissions within, like USNC. But coming to a URSI flagship meeting, you automatically become a corresponding member of URSI Central, and then there is a possibility to apply for senior membership. And then there is also the fellow level. So as we heard, technically we are divided into 10 commissions, and there is a heavy archaeological, layering behind those 10 commissions. So if you read the history of URSI, we started more than 100 years ago, and you know that time the telecommunications was starting. Marconi and others had the telecommunication wireless innovations, and that's why we had the connection to the amateurs, the radio amateurs. And then of course also Marconi had a connection between Europe and US, which was very strange because world is curved, and people, theoreticians, said that no, you cannot have a connection because don't you know, do you believe in flat earth? But he didn't, I guess he believed in flat earth because he tried and he managed to get the connection. So, but then as you know, then we learned about ionosphere, and that's why we have in this 10 sessions, there is a very strong connection to the telecommunications, electromagnetics, antennas, radars, and so on, but also on the geophysical things like ionosphere, and then of course, Commission J, we have radio astronomy. You know that our place in this universe is we know about that due to the radio astronomy. I mean, 3 Kelvin background microwave radiation, pulsars, black holes, quasars, and all of that. Without the radio astronomy, we don't know about that. So that means that we both have quite a broad view of how radio waves, electromagnetic waves, are used, are understood, and used to understand our relation to not only to the universe, but also, say, to the biology, like Commission K, which is the newest commission there. So we live in 3-year periods, as we heard. So think of 3 years. That is, cycle is 10 nanohertz. So it may sound a very low frequency, but at least to me, 3 years have gone very fast. So we have our General Assembly, which is coming this year, August, in Poland, and then remember to come here, and all the young scientists apply for Young Scientist Awards. So we will have great fun there, and of course then we will elect our new board. We will have the council meetings and of course the scientific symposium. That is always 3 years. And then in the mid-years we have, as you know, the Atlantic Radio Science meeting, again coming 27 in Gran Canaria, and then we have the Asia Pacific, which was just held in Sydney in August, and will be then next time in 28 in Toyama, Japan. We also then do have the publications. You know about that. Please remember to submit your papers into our radio science letters. Follow our newsletter. I hope, and I just reminded Mike and Jemesina that perhaps we would like to have some photos of this meeting also to our next newsletter. And then we also have the Radio Science Journal, which also has the other pillar in the geophysical side. Of course, we mentioned about the wires, women in radio science, and I look forward to coming to your meeting in this USNC-URSI meeting, and of course, Young Scientist programs. So go to our websites and please keep your activities within the, also in addition to the National Committee, also with the Central URSI. Thank you.
Good morning, everyone. It's an honor for me to be here. It's also my first NRSM, by the way. I never attended this, though it was on my radar. I would like to thank Michael Newkirk, as well as Professor Jamasina Simpson for inviting me here. Of course, we have very strong relationship between APS and URSI and USNC for a long time through our conference and all those things. That's also reflected by 5 or 6 presidents of APS present in this conference. So with that, I'll try to keep this as short as possible. Let's see. Okay. Yeah. So most of you already know IEEE is now it's 500,000 members strong, and in many countries, I guess. As in history, it started 140 years ago. Now I think maybe 142 years ago. And IEEE has many societies that cater to various technologies, around 39 societies that we have, plus of course 7 to 10 technical councils that we have. APS belongs to one of them. And of course, APS started 75 years ago. Now it's 77 years. In 2024, we celebrated 75th anniversary. Originally started in 1949 by Lester Van Etta. And of course, in 2024, we celebrated the 75th anniversary under the leadership of Professor Branslow Natoras in Florence. Of course, after so many years now, we are 16,000 strong members in APS, 300 plus chapters all over the world. And also we have many publications, around 10 publications, 4 of them are fully sponsored by APS. And of course, 40 plus conferences we co-sponsor, including this conference here. We have many awards in APS, that's around 40 plus field awards, but also 350 fellowships and scholarships for students in APS. So in journals wise, these are the 4 fully sponsored, APS-sponsored journals. You can see the impact factors. When you compare with the similar journals in IEEE, this is one of the highest impact factors that we have. Antennas and Propagation magazine for general reading, Transactions on Antennas and Propagation, and Open Journal on Antennas and Propagation, OJAP, that's an open access journal, and also Antennas and Propagation, Antennas and Wireless Propagation Letters, AWPL that we call. It's a letter, so it's short papers that you can submit to them. And then we have around 6 co-sponsored journals as well. It's a total of 10 of them in APS. And we have a distinguished lecturer program, around 13 of them now active, and any chapter can invite them. They can personally come and give talks at various chapters worldwide. And we have very active workshops, I guess, APS, the distinguished lecturer workshops that are going on right now. Then, of course, we have a very popular program in APS called Young Professional Ambassador Program that has been started in 2022. Each year we select 10 or so young professionals, and they give talks virtually across the world in various chapters. And we actually won the IEEE Young Professional Hall of Fame Award for our activities in young professionals. Of course, recently also we started a APS Talent Development Fund to encourage donors to provide money, donate money to the APS Talent Development Fund that's matched dollar to dollar from IEEE. And the impact of it, though it's a very short program that started only a couple of years ago, impact of that you can already see by some of the programs that are already introduced into APS. One of them is Felsen Research Grant that was introduced with a donation from the Felsen Family Foundation. And the other one is Professor John Vlakas travel grant for graduate students. Around 8 students are funded. It's actually new this year. It'll start from this conference in 2026. And of course, with my own name that I invested myself into APS, which used to be 6 travel grants. Now this year, thanks to Talent Development Fund, there'll be 10 travel grants to the conference. And also we introduced a paper award for young professionals in AWPL, Antennas and Wireless Propagation Letters, in the name of Acharya Jagdish Chandra Bose, who was one of the first ones in 1800s to demonstrate generation of millimeter waves and propagation of millimeter waves for communications. Of course, one of the strong connections we have with USNC and URSI is our flagship conference in summer. And it's actually a combined conference that APS and URSI and USNC does that. And this will be in July. And paper submission is right now open. I encourage all of you to submit papers. So you can submit papers to APS topics, around 10 tracks, 12 tracks we have. And also we can submit to URSI all commissions, A to K there. And both of them have one-page abstract option, but also APS has 3 to 4 page paper option, as well as URSI has 2-page paper option that you can submit. I strongly encourage all of you to submit papers. And one of the advantages for students is various travel grants we have in to attend this conference. One is the Raj Mitra travel grant, because I just talked about John Ulaka's travel grant, because my own CJRD travel grant, and APS student travel grant. We give 22 travel grants to students, and the Musgadan Daneshman travel grant, as well as student paper competition. In the paper competition, we select finalists around 20 plus, I guess, and all of them are funded to come to the conference. And then the recent one is industry application pitch competition, just new this year, where if you're a student and you think your idea can be a good industry application, you can participate in this competition. Top 10 of them also will be funded to come to them. Because all of this requires that you be an APS member, and if you're an IEEE member, you can become an APS member with the $1 today, if you like, I guess. And of course, you can follow us on a LinkedIn page, but also the website IEEEAPS.org. And we are here with my friend Adesh Neil from University of Colorado Boulder. See me and Adesh at the booth if you are interested to become a member and want to learn more about APS. Thank you very much for this opportunity.
All right. Thank you both for traveling here and taking the time to join us here at the National Radio Science Meeting. So I have just two quick slides. I wanted to highlight a couple things that are occurring later this week. We have the commission meetings, we have a WIRES business meeting, a WIRES reception. The welcome reception is also tonight. And then Friday, there's the 13th Hans Liebe lecture, generously supported by the Liebe family. So that'll be over the lunch hour at 12:15, and by Dr. Juan Pardo, who's visiting us here from Spain, I believe. And then finally, I'd like to just thank all the people who have contributed to this year's conference. Christina Potterino at CU Conference Services, CU Boulder Conference Services. Colin Mahoney, who is managing all the AV and so forth. CMS, who's managing the website and paper submission and so forth. And then all of us who have helped with some reviewing and session forming and everything. So thank you very much. And so next, I'd like to introduce our first plenary speaker, Dr. Mickey Batson. He has been a program manager at IARPA since March of 2024. And previously, he worked as a research engineer at the National Security Agency Lab for Telecommunications Sciences from 2013 to 2024. Graduated from the Naval Postgraduate School with a doctorate in electrical engineering and an MS degree in communications engineering. So please join me in welcoming Dr. Batson.
Okay, great. Thank you for the invite, Jamesina. A little background. I was here in, I guess it was 2024, 2 years ago. So had some issues not being able to come this past year. So I'm very thankful and glad that you offered me this opportunity to come talk to what we're doing. So just a little background about myself. I'm retired from the U.S. Navy. My job was focused a little bit on signals, communications, electromagnetics, et cetera. The last couple of my years within the Navy became more about computers, networks, software investigations. It was interesting and complex, of course. I ended up retiring in 2013, and I was able to, fortunately, be able to find a good government research job. I became very interested in what was more on my undergraduate focus, which is on the electromagnetic aspects of radio frequency transmissions. Now, luckily, when I started working at this particular group, I found a very interesting project focus looking at very low frequencies. Fortunately, I was able to convince my office into allowing me to go look at that a little bit more. Now, upon arrival there, my focus became very much focused on the propagation modeling of the VLF. I needed to do a little investigation into the software currently being used in that propagation modeling. So I went down to talk to the people that were currently looking at the software. Now I was discovering that the software that was currently being used had numerous propagation modeling software, but it only had one that was capable of going down into these very low frequencies. And that tool was variable terrain radio parabolic equation, Viterbi. It's very capable, but now as it comes up with all research, you need to have something to compare it against. So what I found was the historical software that was being used propagating within this frequency range was long wave propagation capability, LWPC. Well, that became very interesting when I got it to compare against Viterbi. The first version of that I got was it was a little bit old. Don't want to imply that Fortran's not a very valuable computer programming. It's very useful, but it's a little bit difficult when you're trying to load it onto the new computers. There's some software issues with that, and then certainly modern day security issues as well. So I'm sitting in my office struggling with a good solution to that problem of being able to, well, get funding over to the people that were actually using Viterbi. ROSEMAry walks into my office and asks me what I was doing. So I'm like, well, she used to work at this particular location back several years ago, and she's the one that actually provided the funding for my master's degree. She had gone on to become a very highly ranking official within the government. So, well, as you guys can imagine, I was just a little bit nervous with that conversation. Now, after I briefed her on what I was doing, she was very interested in it, and she wanted to go down and talk with the developers of the Viterbi. As we left that, she provided me the initial funding to be able to incorporate LWPC and compare it with Viterbi. And I say that was a very nice addition to that particular software because the software being upgraded with LWPC became much more capable at modeling these low frequency transmitters. That's not to imply that Viterbi is bad. It just requires a pretty good bit of knowledge of the actual transmitter, which you do not necessarily need with LWPC. So unfortunately, she passed away while I was doing this TDY at this particular location. I feel very obligated to her for what she did with her support. Now, the research that she supported got me very interested in the D region of the ionosphere. The VLF transmission seemed to still propagate when the D region goes away at night. Uses the bottom part of the D region daily, and it still transmits at nighttime. And clearly, some transmitters are they're transmitting at a time where the D region is not over the top of them, and it's going to a receiver that the D region may be there. As you can see here in the graph, it still goes, but it certainly changes that propagation. One thing that's interesting about this propagation that's shown here, it's only one specific direction. So when you start changing the way that those transmissions are being, like the degrees, it definitely changes. It's very interactive with the ionosphere. So I started looking a little bit more. I wanted to pulled a string to take a look at the ELF frequencies. Well, as it turns out, neither of those softwares are capable of really supporting below 10 kilohertz. I'm like, well, goodness gracious, why is that the problem? Well, as it turns out, there's a lot of atmospheric chemistry and a lot of different temperature changes that start affecting frequencies at these lower levels. So I'm like, okay, well, that's very interesting. And fortunately, I was able to convince my current group, well, that sounds interesting. So let's see what we can find out. So now, in total respect for ROSEMAry, I reversely created the acronym, Remote Observation and Sensing of Electromagnetic Anomalies, ROSEMAry. Now, when I started really doing that investigation and taking a look at it, I was found that the only electromagnetic events that I could sort of find that had been conducted about this portion of the atmosphere was based on lightning and meteors. Lightning is a common phenomenon we have all experienced, but nevertheless, it does have some scope on and impact on the planet. Lightning is a dramatic, large-scale natural example of a dielectric breakdown. Charge separation in the clouds create enormous electric fields. When this field exceeds the dielectric strength of air, a rapid discharge occurs, creating a superheated plasma channel a few centimeters in width and several kilometers long. Lightning transfers between 1 and 5 billion joules of energy per stroke, occurring millions of times daily within clouds and between clouds or to and from the ground. Spherics, short for atmospherics, are the impulsive signals emitting by lightning. The frequency ranges from a few hertz to millihertz or megahertz. The spectrograms of spherics are characterized by vertical lines of the frequency time, indicating the simultaneous arrival of all audio frequencies. The sound of the spherics consists of sharp crackling noises like twigs snapping or sizzling noises like bacon frying. Spherics are caused by lightning strokes within a couple of thousand kilometers of the receiver. The VLF radio signal is ducted to the receiver in the Earth ionosphere waveguide. Lightning is a primary contributor to the global energy balance of the Earth ionosphere system, acting as a crucial battery of sorts that maintains a potential difference of about 200 to 300 kilovolts between the Earth's surface and the ionosphere. The potential difference drives a continuous, small, downward, fair weather current everywhere across the globe, completing the circuit. Lightning also contributes to the atmospheric chemistry. The immense heat disassociates nitrogen and oxygen molecules, creating reactive nitrogen oxides. These chemicals are critical to the production of ozone and hydroxyl radicals in the troposphere that act as a cleaning agent of these greenhouse gases like methane. Lightning also generates electromagnetic pulses that propagate the Earth ionosphere waveguide, forming the Schumann resonance, which can provide insights into global lightning, disturbance, weather, and electrical state of the atmosphere. But lightning charges, as I mentioned before, they're not the only energetic phenomena that are occurring within this part of the atmosphere. There's approximately 44,000 tons of meteor debris that collides with the Earth on a daily basis. Now, nearly all the material is vaporized in the atmosphere, leading to well-defined metallic layers between the 85 and 105 kilometers of the atmosphere. These dense temperature clouds significantly impact radio communication and navigation systems. They also couple with atmospheric winds and tides, linking the troposphere and the mesosphere with the upper ionosphere, allowing lightning discharges to impact the metallic layers above. About 5 kilograms of meteors release about 6 billion joules of energy, primarily into the ionosphere. That's about the same amount of energy of a large lightning discharge. It has been recognized for hundreds of years that some meteors, like some aurora, produce sounds. Edmund Halley briefed at the Royal Academy in 1714, and even then it was recognized that light traveled faster than that sound. So how could a far distant and transient event like a meteor be visually observed and heard at the same time? Now, eventually the phenomenon was called electrophonic effect to this day. Now, that's not part of this brief, just thought I would mention that for everyone. There's still the main focus, and there is still a consensus on the existence of meteor electromagnetic emissions and their impact. Our focus in ROSEMAry is to analyze data from global ELF and VLF receiver stations and thermal and optical images. We will try to determine if and how meteors interact with the ionosphere plasma to produce low-frequency emissions and how such emissions can advance our understanding of the ionosphere, specifically within this 50 to 100 kilometer part of the atmosphere. It's well established that lightning-generated spherics can be and are actively used with tomographic inversion techniques to produce detailed maps of the ionospheric properties, particularly in the D region. We believe electromagnetic transients produced by meteor shock wave interactions in the lower ionosphere could improve estimates. So a little bit more about the atmosphere, the Earth ionosphere waveguide. So global observations of ELF and VLF transients within the Earth ionosphere waveguide have been used for remote sensing properties of the relevant source mechanism. Measurements at multiple locations around the globe can triangulate the impulses and can be used to determine whether widely varying spectral content triangulates to the same location. Now, to date, different ELF, VLF transients have been identified. Q-burst exhibited only ELF content below 3 kilohertz. N-burst exhibit ELF and VLF content that triangulate to the same location. And VLF burst, which exhibit only VLF content, thought to be associated with, but no ELF content. This was reported by Flint et al. In 2024. Now, each of these established ELF and VLF transients are thought to be associated with lightning or lightning-related phenomena, as the example is shown here in the N and Q burst are shown here in the slide. These types of transients have not only been used to investigate the properties of the relevant source current, but also the propagation characteristics have been used to remote sense properties of the lower ionosphere, and this was reported by Golowski et al. In 2018 and McCormick et al. In 2018. At present, research continues to produce reasonable results of the ionosphere properties that can reproduce observations. The state of the art lies in producing new ionosphere inversion methods that account for spatial and time variations. It is well established that ELF and VLF signal amplitude and propagation phase are used to remote sense the lower ionosphere. Recent important work demonstrate the excellent additional utility of observed ELF, VLF signal polarization, and based on these results, it makes sense that ELF, VLF wave impedance would also contribute to the problem. Now, this fact has not yet been rigorously established, however. The use of VLF signal amplitude dates back to like the 1960s and earlier, and some use of VLF signal phase started reliably being used in the 1980s and the 1990s. Phase measurements are now commonplace, thanks in part to GPS reference clock stability, but they still come with a set of complications due to signal modulation effects. Recently, measurements to remote sensing of the lower atmosphere, Birch and Moore in 2022 and 2024. Birch and Moore in 2022 demonstrated that polarization analysis can be used to detect VLF propagation nulls, which are sensitive indicators of the ionospheric parameters. Birch and Moore in 2024 investigated the use of Stokes parameter polarization in the analysis of transient ionospheric disturbances and attributed physical changes in the scattering body to observed changes in polarization. Furthermore, Birch in 2021 demonstrated that the Stokes parameters are especially sensitive to the properties of the overlying ionosphere. In fact, Birch in 2021 demonstrated that signal polarization, as measured using Stokes parameters, did not suffer from the different difficulties associated with phase demodulation, resulting in a higher SNR measurement, and proved that signal polarization added meaningful new information about the ionosphere in addition to amplitude and phase. Some theoretical work on wave impedance indicates it may have a similar importance for remote sensing. The combination of signal intensity, propagation phase, wave polarization, and wave impedance likely impacts the interpretation of the properties of the ionosphere. Challenging problem. Remote sensing to the exact density profile of the lower ionosphere is difficult to perform because it is an ill-posed problem. Many solutions can produce the same result in terms of the amplitude and phase of the observed signal. For this reason, researchers use probe signals at multiple frequencies and sometimes make use of signals coming from different directions in order to obtain as much information about the ionosphere as possible. Now, to simplify the problem of ionospheric remote sensing, many investigators have used parameterized models of electron density as a function of height. This was Thompson in 1993, Kummer et al. In 98, and Moray et al. In 2012. The only generalized manner in which the region can be probed is using the ELF and VLF radio signals. Rockets can directly measure the properties of the region for a brief time. Most satellites fly too high, and balloons do not fly high enough to in situ measurements of this 50 to 100 kilometer part of the atmosphere. Other radio frequencies cannot assess vast regions around the globe, around the world in a controlled manner. As a result, at present, the most impactful measurements of the evaluating the properties of this lower and upper limit of this part of the atmosphere are measurements of the ELF and VLF signal propagation. So now, as previously mentioned, the only research that we were able to find about this part was related to lightning and meteors. So for lightning, we found that lightning channels behave like huge antennas that radiate electromagnetic energy and frequencies below 100 kilohertz. The signals are very weak at large distances from the lightning source. However, the Earth ionosphere waveguide does behave like a resonator at extremely low frequencies. There are also positive strokes. Positive lightning is rare. It's about 5% of lightning that can carry up to, but it can carry up to 1 billion volts or 300,000 amps. The potential difference between the ionosphere and the Earth is maintained by lightning strikes, delivering negative charges from the atmosphere to the ground. So for meteors, the vast majority of meteors, of estimated millions of meteors that rain upon the Earth daily, are the size of a grain of sand. These meteors still pack considerable energy by virtue of the speed, about 200,000 joules. But that's 10 times the muzzle energy of a 50 caliber machine gun bullet. Only about 0.1 to 10% of the energy is released as visible light, with most dissipated as heat. When large meteors scale kilograms or more enter the atmosphere, they begin to ablate and fragment. About 5 to 10% of this kinetic energy is converted to total radiation, not just visible light. We believe an incoming meteor produces separation and accelerates electrons. These are the two ingredients for an electromagnetic emission. The meteor's maximum release of electromagnetic energy within this part of the atmosphere occurs at the greatest rate of change of the kinetic energy. When a meteor hits the upper atmosphere at about 60 kilometers per second, a strong bow shock forms. The meteor begins to ablate, and the wake forms. Temperature at the stagnation point easily exceeds the ionization temperature for ablated materials. Additionally, instantaneous temperature changes through the strong shock wave further ionizes atmospheric gases like nitrogen and oxygen, and water vapor, which is found in the D layer, creating ionized classes like nitrogen oxide negative and H3O positive. Heavier ions get swept along the meteor, but electrons are magnetized and move along the magnetic gradient. This causes a charge separation. Free electrons in the ionosphere are accelerated through shock interactions and also by fragmentation and irregular ablation. The free electrons will continue to stream through the ionosphere until they lose most of their energy and become part of the thermal plasma. When a free electron streams through the ionosphere plasma to collisions with charged particles, disturbs the electric and magnetic fields, producing short duration transits. Alternatively, depending on the Knudsen number and altitude, turbulent eddies and vortices from along the electron density enhanced weight, the motion of electrons in the geophysical field could potentially give rise to low frequency emissions. Okay, deep breath, that's the theory. So now let's take a look at some of the data. So based on the research, we initially found that lightning and meteor demonstrate different spectral content. Lightning is stronger at greater than equal to 5 kilohertz, and meteors are stronger at less than or equal to 2 kilohertz. Now, unfortunately, you can't predict the exact time of lightning or the exact time of a meteor shower, but in general, where we're at in Virginia, August is the lightning season. I'll cover that just a little bit more. Also, there are several meteor showers that occur every year. Perseus in August, Ornids in October, Leonids in November, and Geminids in December. We hoped our initial measurement would allow us to model the phenomena and understand the complex interplay that give rise to electromagnetic signatures that can be sensed terrestrially. Perseus was good, at least I thought it was going to be great. We had both lightning and meteor events occurring frequently, and the other event was useful because just the meteor events were more prevalent. Now, fortunately, we had some low-frequency equipment. It was a Matronics induction coil magnetometer. It's a delicate, sensitive instrument, and a farm willing to host us. So some of our initial results, fortunately, I was able to give a brief on this result in FY23 here, so that at this particular conference. It was limited. The challenge when you're not exactly sure what the electromagnetic field looks like or the frequencies that are being created, that limits the use of filters and signal processing. Another challenge is the most readily available data base of visual observations of meteors reported by the American Meteor Society is not synchronized to GPS. Lightning spherics overwhelmed us. This is my response about the August. The lightning during August overwhelmed by orders of magnitude the number of expected meteor-generated spherics. So correlation was a little bit difficult, and also based on the limited equipment that we had, we were being compounded by low-frequency AC harmonics. Now, one initial filter that we did apply was the AMS data. We only considered meteors being reported by at least 10 or more people. This did provide a slightly more reliable time reference and gave us an approximate trajectory and distance from the instrumentation. Now, on one occasion, we had GPS referenced NASA Skycam video of meteor on the East Coast. This provided our first unambiguous correlation between terrestrial magnetometer measurement and a visual meteor signature within the visual line of sight. We were able to get a validation of what we captured through NASA. The validation was very beneficial. The NASA confirmation is more accurate than AMS. Thank you very much, NASA. So for FY24, that was nice. We were fortunate able to upgrade our system. We increased our reception and our signal processing for the FY24 observations. Our new signal reception apparatus consisted of 2 orthogonal 3.5 meter diameter loops oriented north-south and east-west. And we also were able to get data from highly sensitive and calibrated instrumentation thanks to Professor Rob Moore and the University of Florida Ionospheric Radio Laboratory. And fortunately, we were also able to get optical reception capability. We applied what we had learned in FY23 and applied new filter and signal processing knowledge to be able to focus on the lightning and meteor events. Now also, thanks to Professor Rob Moore, we were able to expand our review we were able to expand to previous observations for comparison and study of what we were looking for. So, as I said, we were limited, unfortunately, we were only limited to August in FY24. But as previously mentioned, both filters and signal processing work great when you have a good idea of what you're looking for, as seen in the graph here. We had a good idea of what our meteor electromagnetic signal was going to be looking like. Now, however, as I said before, when you're doing research, you don't know exactly what you're looking at. You have to use, filters and processing need to be kind of used wisely, as well as the time that the event actually occurred. So now, for example, here in the slide, we were able to estimate the angle of arrival of the signal by comparing the phase of the disturbance detected by the north-south loop relative to the east-west loop. The Perseid shower is so named because the incoming meteors appear to radiate from the constellation Perseus, but in reality, it's the debris from the comet Swift-Tuttle. Now, from Northern Virginia, the constellation of Pegasus is low on the northwest horizon, with meteors moving to the southeast. Analyzing several events where there are dozens of AMS observations, reports resulting in angle of arrival estimates that indicated the source of the emission was to the west-northwest of Virginia-based array. So now, as mentioned before, Professor Rob Moore, we gained access of U.S. satellite detections of lightning discharges from earlier years. We identified a record of an intense and long duration, about 1 second, optical signature off the southern coast of Madagascar in August 2016. That was identified by the Center for Near-Earth Objects as a massive bolide. The optical spectral intensity was atypical for lightning and was identified as a bolide 2016-224. We checked data records of ionosphere radio laboratory collection at Palmer Station and Arava Heights in Antarctica. At the exact GPS-based time, the optical bolide signature was detected. Very high amplitude emissions were detected spanning the range between ELF and high VLF. The emissions were detected at both Palmer Station and Arrival Heights, giving us which is a baseline of about 5,000 kilometers. This signature, simultaneously collected by two receivers with an optical radiant intensity profile, represents the most compelling evidence of an electromagnetic emission from a large meteor. This figure here shows a typical lightning-associated ELF-VLF transits. On the left, the large frequency, or the large spherics, are clearly visible in the intensity and the direction of arrival, exhibit wide swaths. Now, on the right, the much shorter integration time results in a much narrower impulse that appear to fade into the background of the noise. Now, this shows the same analysis of the meteor event in the ELF-VLF transient. Now, in the left, the ELF and VLF transient intensity and direction of arrival appear the same as those of the lightning. In the right, the shorter integration time reveals the signal intensity persists and the direction of arrival persists despite the short integration time. The meteor-associated Stokes direction of arrival signatures can be visually detected, implying that a simple algorithm can be employed to detect meteor and automatically distinguish a meteor from lightning-related spherics. Professor Rob Moore will discuss this later in his briefing later. Now, on the right is the optical signature of the bolide 2016-224. Impact on the ionosphere is shown with the GPS timing that aligns with our ELF-VLF observations. So now, based on our limited set of observations, it appears that the ELF and VLF transits associated with meteors indeed have a peculiar signature. Unlike lightning-related phenomena, the transit appears to have wide spectral content, and content appears to persist at all frequencies for a prolonged period of time. Now, nevertheless, it is difficult to see the result by simply inspection of the signal amplitude. The signal at all frequencies dissipates rapidly with time, just not as rapidly as that with the lightning charges. We have observed and reported that bolide 2016-224 signature can be distinguished by the application of the nonlinear processing. The direction of arrival of the impulse can be calculated using the Stokes parameters. The direction of arrival does not depend on the signal amplitude specifically. And now, as a result, as long as a signal persists and is coming from the same direction, the Stokes direction of arrival is detectable above the noise floor. One of the important conclusions formulated in 2024 was that the Stokes direction of arrival associated with bolide 2016 appears to persist at all frequencies for longer periods of time than those associated with the ELF and VLF transits associated with lightning. So now, as a side note, so based on the discovery, we started expanding our thoughts just simply beyond the ionosphere and sort of really adding and investigating the atmosphere, specifically the mesosphere, which is 50 to 100 kilometers. Interestingly, that's the same estimation of the D region during the day, but the mesosphere is always considered present even at nighttime. Mesosphere is the third layer of the Earth's atmosphere, directly above stratosphere, and it's below the thermosphere. I will say the temperature gets extremely low in this, almost down to below negative 143 degrees Celsius. The low boundary, based on the geography, the latitude, the low boundary is usually about 47 to 51 kilometers, and the upper boundary is about 85 to 100 kilometers, which is very similar to our D region. So on our discussion, we want to expand our research in order to gain a better, accurate understanding of this electromagnetic creation within the lower atmosphere. So the ROSEMAry focus will be to investigate if high kinetic interactions between meteors and the ionospheric plasma generate electromagnetic disturbances, and if so, determine the physical mechanisms and give rise to the emissions, and if ionosphere source currents implied by terrestrial ELF, VLF measurements could improve our understanding of the lower atmosphere. The primary focus is on determining when meteors create electromagnetic disturbances, what specific factors give rise to the emissions, the mass, speed, composition, shape, etc., and can the emissions be mathematically described and statistically compared to observations in terms of frequency, amplitude, and polarization. Bottom line, create a relevant vertical, horizontal, and time theory for the most accurate understanding of this part of the atmosphere. An ideal data set related to the low-frequency electromagnetic waves would include high temporal, spectral, and spatial imagery from an object to the point where the electron count approaches ambient and the velocity gradient is zero, would help identify turbulent structures, temperature, pressure, and volume gradients across the wake. We believe this imagery would be extremely helpful in understanding the causes of the low-frequency electromagnetic waves, specifically the shear instabilities, plasma oscillations, and recombination of electrons. We conjecture that meteor spheric add important information to an inversion process because unlike lightning, which is localized to a few kilometers, a meteor source current could extend many tens of kilometers. Now, gaining this knowledge related to the electromagnetic waves within the vertical, horizontal, and the time of day for this part of the atmosphere would be required for the following: developing a robust understanding of the interplay between numerous complex phenomena that create low-frequency electromagnetic waves, calibrating and improving computational tools to predict the nonlinear interactions, forming an objective standard by which the feasibility of novel electromagnetic sensing concepts can be gauged. Additionally, detailed understanding of objects affecting this part of the atmosphere may operate in other parts of the atmosphere. For example, just below the mesosphere, shock waves, pressure gradients, and turbulent wake structures interact with this part of the atmosphere. The assumption of the displacement of free electrons in the mentioned example could possibly give rise to electromagnetic signatures and detectable changes in the propagation of natural electromagnetic waves. A data set of the atmosphere scintillation, free electrons, ducting, and propagation of these examples will certainly provide valuable to quantify the following: the height, width, part of the atmosphere interactions and the time of the occurrence, effect of the projectile interactions on the propagation of natural occurring height of the atmosphere wave phenomena, and propagation of a plasma wave related to this part of the atmosphere and the time of day. So the strategy: analyze optical and low-frequency electromagnetic signature, specifically duration, frequency, rise time, amplitude, polarization. Estimate source current implied by terrestrial measurement, accounting for propagation effects. Establish a definitive assessment of electromagnetic waves. Evaluate different physical mechanisms to determine the following questions. Is it possible to match source current and other signatures? Signature parameters. What is the most likely cause of the emissions? What triggers the emissions? What limits the emissions? Our team: primary investigator, scientist Nick D'Angelo at ARLIS, organize and coordinate the strategy. Professor Moore, he will be investigating EPCOTs of publicly available low-frequency electromagnetic data sets captured by receiving locations, starting 2010 to present. As I mentioned previously, Arrival Heights and Palmer Station in Antarctica, but also including Gagana in Alaska and Sandrostrom in Greenland. Perform analysis on other transient events. Go back and include the rest of the 2024 meteor shower events. The Cheroblinsk bolide that occurred in February 15th, 2013. The Bering Sea bolide event that occurred in December 18th, 2018. And then other events that could be collected by space-based optical systems that are atypical for lightning discharges and suggestive meteor events. Lead a propagation modeling effort to estimate the ionosphere source current necessary for the low-frequency electromagnetic impulses received to provide insight into those low-frequency wave phenomena mechanisms. Professor, clicked the wrong one. Professor Alex Mamyshev, University of Washington, obtained raw optical images from GOSR-R and other space-based lightning sensors and segregate spectral intensity profiles of typical for lightning from atypical spectral intensity profiles that may be associated with meteor collisions. Oh, man. Sorry. Professor Bob Marshall here at the University of Colorado used finite difference time domain full wave electromagnetic code to predict the low frequency electromagnetic propagations in this lower part of the atmosphere. Certainly collaborate with the team, produce an analytic electromagnetic source model that is consistent with experimental observations of meteors and provide an ionosphere propagation model for electromagnetic emitters of this part of the atmosphere. Oversee and direct the effort to numerical implement meteor-related currents as sources in this part of the atmosphere that produce low-frequency electromagnetic waves. Professor Bhuvani Srivansh at University of Washington. So she will obviously collaborate with our team, but she will look and test the hypothesis that vortex shedding and eddies at the meteor wake and mesospheric plasma boundary produce pressure fluctuations that couple with the magnetic field fluctuations that lead to a low frequency electromagnetic emission. Create numerical simulations of turbulent flow around the spherical and highly angular wedge to quantitatively understand fluid and magnetic field spectra in the height, width, and time of day. Apply perturbations to the flow to create fluctuations and understand their impact on the electromagnetic emissions that may be produced. Oversee the implementation of production loss terms to approximate the impact of the ionosphere and recombination on pressure fluctuations in and along the meteor wake. and the connected effect on electromagnetic emissions production. Professor Mears Oppenheim lead an effort to develop a realistic analytical model for the generation of currents in the ionosphere by the impact of a large body, such as a 10 to 100 kilogram meteor, leverage the previous research that we're investigating small meteors at upper atmospheres, develop an approach to solving the analytical relations developed numerically to predict low-frequency electromagnetic radiation generated by meteor-induced currents. So, as you can see, we have a busy year. We fortunately have been able to establish a very strong team that is qualified, welcome, and needed to investigate an unstable portion of the atmosphere. The physics and chemistry of this part of the atmosphere changes daily, hourly, vertically, and horizontally across the sky, across the earth. Our goal is to gain a better understanding of the causes of these changes, and create ways to detect and even anticipate these atmospheric changes. So, based on your questions, this concludes my presentation.
Yeah, we have time for questions. Please go up to the mic. There's a mic right here.
Hey, excellent presentation. Thank you very much. I had a quick question about the polarization characteristics of the ionospheric waveguide. I'm not super familiar with the science behind that, but is there a particular polarization favored through that waveguide?
I don't think there's a particular one. I think it changes because the chemistry and electronics, or the electrical field is changing based on where you're at. And
Thank you.
That's Professor Moore. He was asking about the change of the polarization. Does that occur? Yeah.
Go ahead and ask again.
I was just interested if there was like the signals that you see in this ionospheric waveguide, if they're particularly polarized in any which way.
Most of the time, they're polarized linearly, like under daytime conditions. If
Oh,
you have
okay.
a vertical impulsive signal that's propagating through the ionosphere waveguide, it's largely linear. It's TEM almost.
Oh, awesome. Okay.
Almost. And then nighttime comes around and it's not anymore. And so you can't really do direction of arrival very well at nighttime under these conditions. Daytime is pretty good most of the time, not always. But nighttime it's not. And so you have to account for the effects of the waveguide.
Okay, thank you.
So Mickey, excellent talk. I really appreciate it.
Thank you.
I've already received a number of text messages asking if it has a possibility of leading to, this program has a possibility of leading to any future larger programs, and if you wanted to talk about that at all today, because other people are very interested in contributing to this work.
Thank you. I'm not sure I have answers to that particular question on how far this project will get extended. I think that's certainly based on the no kidding real data that we have gotten and analyzed, and then further, advertise that in a sense. That's not the correct word to use, but once we've collected, once we've analyzed it, we can then demonstrate that, yeah, there's some real validity to what we have been investigating. I know that's not an exact answer to your question, but I can't really, what's the potential? That's what we're trying to find. That's why it's a research, of the science. Yeah.
Thank you. Great talk. And the meteors part was really interesting because it sounds like it brings in not only a perturbation to what you're trying to study, but also a new source signal, right? Which the source signals are really the challenge here. Have you thought at all about controlled sources, which of course are very challenging to radiate at those low frequencies, but there are some, right? There's a 82 hertz Russian transmitter that's been more active recently. There's also ways of generating very low frequency waves and ELF waves with, for example, ionospheric heating, HAARP facility in Alaska. Do you see room for kind of controlled sources in helping solve some of these problems?
I'm up for, this is new, like kind of slightly answering his question and answering your question, open for, many different ways of getting sources and doing the analysis. I would say the big thing that we're trying to sort of get a better understanding of is the horizontal changing of this part of the atmosphere. A lot of measurements are done straight down or straight up. And horizontally, especially when you're talking about VLF and ELF transmissions, I mean, that transmitter is in one location. It's transmitting to a receiver that's nowhere near. It's going very horizontally. So yeah. Yes.
Good morning. Excellent presentation.
Thank you.
Indeed, I enjoyed it very much. I have two questions. One is about communicating through the atmospheric ducts, which change with time and day. And there's a lot being done on that. And I'm wondering if some of your studies, also, or some of the interest extends to finding the right frequencies, finding the right time to communicate, and things of that nature. So that's one of the questions. I do have a subsequent question relating to modifications of the signals, which can be used also to code or to detect and to be able to, retrieve data when with much better clarity. So these are, you can answer. I don't expect that
A complete,
the second question can be answered. So I'll leave it up to you. So
So I would say that a lot of what we have done initially, the research for the research, where there's just was not a lot of observations of how the D region area of the atmosphere was affecting different communications, different electromagnetic occurrences that are being created within that part of the atmosphere. I'm not sure that really answers totally your question in terms of the frequencies of transmission, but any other capabilities of being able to analyze data, that would be very beneficial.
Good morning. Thank you. I have one quick question, I hope. Given the significance of this globally in the proliferation of space sensing, do you have any comments today on how you would go to three-dimensional sensing outside of, beyond terrestrial?
No, I have no answer there. There's one of the aspects that we have sort of maintained is what we're trying to research is how can you sense this terrestrially at these very low frequencies across the earth instead of being in one place. That's kind of what the focus is initially. I'm not saying that it wouldn't eventually go with what you're referring to in terms of a three-dimensional. I would think that would be certainly ideal. But right now, our little basic research to get started is, really the determination from a terrestrial type of receiving system. No, thank you.
All right, so every triennium, we give out a few USNC-URSI awards. Each of these is given to one recipient every 3 years, so it's quite an honor. And so since this is the last NRSM of this triennium, I'm pleased to be able to give out the awards for this triennium. First, we have a Distinguished Radio Science Award. This award was created to recognize significant contributions to radio science made throughout an entire career. And this triennium's recipient is Dr. John Balakis for contributions and leadership in the field of electromagnetics, including computational methods, antennas, and biomedical sensing. So I know you're in the audience, so if you're able to come up for a moment, we'll give you your award, and you're welcome to say a few words.
Okay, well, first of all, thank you, Jamasina. Thank you for to the people who nominated me and the people who wrote. I'm sure they wrote some reference letters as well somewhere along the line. I would say I'm indebted, incredibly indebted. I've been coming to this conference since 1984. I have never missed one. Probably my wife is not as happy about that, but I have never missed one. So it's been, and as you know, I served also as chair of the Commission B as well, and both of the Commission B International. And it's been part of my life. My students also always presented papers here every year since 1984. For me, I want to say that this place has been part of my family. This community has been part of my family. So getting a recognition from the people that I've lived with for almost 45 years, I'd say more than 40 years, is incredibly, incredibly pleasing and humbling. I never thought that I will be here today. When I started to the students, I would say, just keep at it. Find a good problem that nobody else has solved. Don't try to add to a problem. Maybe you can learn and add little things, but also try to solve problems that have never been touched before and be patient with it. You'll get it. So I also tell to people that without trying a new problem, you're probably not going to make an innovation. So I think I've been fortunate to have 115 PhD students and have extremely good relations with them and have done well. And they all like to solve challenging problems. So I want to continue contributing to this. So this is not the end of my career. And I know that it feels that way. It actually, my heart pulsates when I think about that. I want to thank the many, many, many people that I work with. I see here Notaros. I see here CJ. We work together in many different ways. I see many of the URSI, leaders here that I've worked with left and right. I look forward to participating and co-chairing the technical committee in GAS 2026. It's been a pleasure to do that. I continue to have endless energy, just like you, Jamasina, and many other people here. So it's been a pleasure, and it just feels so good to be here today, and it feels so good to be part of the recognition and this community. Thank you.
And in recognition of your award, we have a plaque that you can take with you. And so we'll.
Oh, it's very light. It's extremely light. I thought this would be something from a seashell.
And we'll take a picture over here. Next, we have the Outstanding Educator Award. This award recognizes outstanding education career achievements by a distinguished educator in the field of radio science. And criteria for the award include excellence in teaching, effective mentoring, curriculum development, authorship of course material, and educational contributions to the profession. And the recipient for this triennium is Dr. David Jackson for education and mentoring in the areas of microstrip antennas and leaky waves. So, David Jackson.
Thank you, James Sina. Well, I'm very, very proud to be a recipient of this award, partly because it's coming from one of my favorite organizations, USNC-URSI. First of all, I'd like to thank, first and foremost, my nominator, Rehan Bakhtur. I really appreciate her confidence in me and her nudging me on for this. Her support has been fantastic. And I'd like to, of course, thank my reference writers. That includes Dr. Stuart Long, Stephen Weiss, and Gary Brown. I really appreciate the fact that they took the time to write the letters for me. And I'd just like to say that, part of the value of this award is that it's related to the area of mentorship. And that's something that I really strongly believe in. And I hope that all of us choose at some point to become mentors, because it's really such a valuable thing that we can do to the younger people in our community. Now, I myself am honored to have one of the best mentors that anybody could ever have, and that would be Professor Arthur A. Alliner. For those of you who don't know that name, he's the pioneer of leaky waves and leaky wave antennas. I first met him back around 1984 when I was getting ready to graduate, and I was going on different interview trips. And one of the places I went to was what was known then as Brooklyn Polytechnic Institute, where Professor Alliner was, together with Professor Felsen and Professor Markovitz, and had a good time there. I didn't end up going to Brooklyn Poly, but the best part of the trip was I met Professor Alliner, and he became my mentor and collaborator for more than 25 years. And I can't emphasize how important that was on my formation as a researcher. The countless times, for example, that I would meet him at conferences, including this one, and we'd be meeting in the lobby of a hotel till after midnight talking about leaky waves, or the times where we'd have phone conversations. I remember one phone conversation that lasted, believe it or not, 8 hours. I had to take a break during lunch. It was broken into 2 parts, the whole time just talking about leaky waves. It just doesn't get any better than that. So for the young people out there, I hope you have an opportunity similar to that, to meet such a fantastic mentor, and that will really guide your formation and your career, I hope. So with that, I just want to thank you all so much for having the confidence in me to nominate me for this award and select me. I really appreciate it. And have a good conference. Thank you.
And we have a lovely plaque for you to take home as well. And we also have the Impact Award. This award recognizes an individual or a team whose radio science work has made a positive impact on the broader society in areas including diversity, inclusion, and outreach in areas relating to radio science, as well as applications of research with societal benefit. And for this triennium, the award goes to Dr. Susan Hagness for transformational advances in microwave diagnostic, imaging, and therapeutic technologies, time-domain computational electromagnetics, and applied electromagnetics education for outstanding diversity, inclusion, and outreach leadership. Congratulations, Susan.
Good morning, everyone. Jamesina, thank you. URSI is a phenomenal organization of research scholars and electromagnetics educators. It's also incredibly supportive as an organization. And I'm deeply grateful to Rick Zolkowski, who nominated me for this award. I'm also deeply grateful to the endorsers. I did not get their permission to reveal their names here, so I'm not going to give them public shout outs, but you know who you are. Really grateful. And I want to dedicate this award in part to some of the supporters from the past decades. There are so many people that come to mind, but in particular, my PhD advisor from many decades ago, Alan Taflov, who's no longer with us, Maria Stuckley, also no longer with us. I also have a special spot in my heart for Wilson Pearson, who kind of took me under his wing when I first started as a graduate student being involved in URSI, and he was the one who nominated me many years ago for the URSI Koga Gold Award. So just an incredible amount of support and community-oriented spirit in this organization that makes it very special and unique. Impact is engineering impact, scientific impact. It's a team sport. And so this award is not recognizing my efforts. It's recognizing a group effort. I've been so fortunate to work with amazing students over the last 3 decades, more than 3 decades, and also collaborators. So a huge shout out to all of them. Thank you again for this incredible honor. I'm really touched.
And we have one more award. This is the Chair's Award. And this is given for it honors outstanding contributions to the work and mission of USNC-URSI. And we learned yesterday that this recipient is unable to be here at the plenary session, so we've decided to give this award out at the welcome reception tonight. So I hope you can join us there. And since our first plenary speaker has already spoken, I want to give a plaque in recognition of your talk. Yes, please come on up, Dr. Batson. All right. Well, I would like to introduce our second plenary speaker, Dr. Paul Ransom. Dr. Ransom is the acting chief of the Strategic Planning Division in the Office of Spectrum Management, and he is chair of the Spectrum Relocation Fund Technical Panel. He served as the technical lead for the 2024 National Spectrum Strategy and Implementation Plan, and began his career at the Naval Surface Warfare Center. He served as a program manager previously at ONR, and served as a chief technologist in NOAA's Radio Frequency Interference Monitoring System Project Management Office. Dr. Ransom has a BS in Electrical Engineering from Southern University and A&M College, an MS from Georgia Tech, and a PhD from Catholic University of America. So please join me in welcoming Dr. Ransom.
Thank you, Jamesina. Good morning. First, I'd like to thank the National Committee for Radio Science for this invitation. I'm delighted to be here to talk to you about spectrum. My name, again, is Paul Ransom. I am the acting chief, like Jamesina said, for the Strategic Planning Division in the Office of Spectrum Management at the National Telecommunications and Information Administration. Lots of acronyms here. Today I'm going to talk to you about spectrum, which is very much a hot topic in my area, and as you know, is fundamental to just about everything we do in radio science as well. Before I talk about spectrum and harmful interference and electromagnetic compatibility, I think it would be helpful to explain a little bit about NTIA and the Office of Spectrum Management. From now on, I'll call it OSM. NTIA is the principal advisor to the President on telecommunications and information policy. NTIA is also responsible for presenting the executive branch view on telecommunications matters to the Federal Communications Commission, also known as the FCC. This includes things like the availability of federal spectrum or transitioning federal spectrum to non-federal use. I'll talk about that more. It's very hot. It's a critical item in the federal government, this idea of transitioning what's known as federal spectrum to non-federal use. But let me also talk about, you can think of NTIA as a president's proxy, delegated the authority to make what we call frequency assignments and authorize the use of spectrum for federal users. So within the FCC is known as a regulator. They regulate use of the spectrum for non-federal users. NTIA is similar, but not the same as a regulator. We authorize use, we assign frequency assignments to agencies, but we're not strictly considered a regulator for federal use. It's an important distinction that we'll get to later. However, in exercising these, well, my office exercises these authorities to make frequency assignments and authorize the use for federal users. And I think I'd be remiss if I said, since we're here in Boulder, I'd like to give a shout out also to my ITS colleagues who are very much an important part of NTIA. The Institute of Telecommunication Science is obviously an office within NTIA, and we in NRSM work very closely with ITS on all spectrum-related matters. So let's dig into what managing federal spectrum kind of means. I've talked about this earlier. How do we manage spectrum for federal agencies? Well, let's take a step back. To operate federal systems and conduct federal missions that require spectrum, federal agencies need what's called a frequency assignment. And that frequency assignment is assigned from the Office of Spectrum Management. So if you think about airport radars, airport surveillance radars, or if you think about weather radars, or you think about space research services, all these different kinds of services and applications require frequency assignments to operate safely and not to interfere with each other. As you can imagine, frequency assignments are all about coordination. A single system needs to operate on a specific frequency or band of frequencies in a specific area for a designated amount of time without causing harmful interference to anyone else, either in the band or adjacent to that band. That's the coordination aspect of a frequency assignment. Kind of makes sense. The process involves coordination and requests and, to ensure that there are no adjacent, harmful interference. This process is managed through something we call, or through a committee known as the Interdepartmental Radio Advisory Committee, also known as the IRAC. I'm going to say a lot of, you'll hear a lot of acronyms throughout this talk, but IRAC is one of the longest serving committees in the government. In fact, it was established in 1922, over 100 years old, obviously. And it includes every department or agency that uses radio spectrum in the government. And along with the departments that use radio frequency spectrum in the government, it also includes the commission as an observer. So in all the coordination activities that we do as a part of NTIA, it's really done through this IRAC process. Beyond, beyond, making frequency assignments, NTIA has another core responsibility that is related to managing spectrum, and that's certifying the systems that operate on these frequencies. So our office ensures that the federal agency's systems conform to frequency allocations. So a frequency allocation could be for a fixed service, it could be for an aeronautical service. So if you ask for a frequency assignment, you have to ensure that frequency assignment is consistent with the allocation where that assignment is going to be used. For example, as I said, operating a fixed microwave link on an allocation means that that service has to be operated in an allocation for fixed services. An agency can't just decide, hey, I want to use this particular frequency band and utilize a system where the application is inconsistent with the allocation. So we make sure that those things are compliant. In addition to ensuring that they're compliant, those frequency assignments are compliant, we also coordinate the system certification with different planning groups within that allocation of the IRAC to ensure the systems and the agencies operating the systems are following the prescribed management policies. So I'll have here's a concrete example. If an agency wants to operate a drone in a spectrum that the FAA relies on, they need to not only coordinate with the NTIA, get a frequency assignment, but they also must work with the FAA's Aeronautical Advisory Group. This is the actual group within the IRAC, to ensure they're fully compliant with the policies of that spectrum and that allocation. It's a complex system that we have to go through to ensure that systems operate, missions are conducted, and they don't cause harmful interference. That's one of the kind of core aspects that NTIA has of managing federal spectrum. Another core element of managing federal spectrum is conducting electromagnetic compatibility studies. So, obviously we coordinate spectrum use, and we also carry out electromagnetic compatibility to see if it's possible to make, again, federal spectrum available for non-federal use. So you may have heard of the One Big Beautiful Bill Act, passed by Congress and signed by the President on July 4th. This bill tasks the NTIA administrator with studying several bands for reallocation. Those bands include the 2700 to 2900 megahertz band, the 4.4 to 4.9 gigahertz band, and the 7.25 to 7.4 gigahertz band. We had to do those studies over the next 4 years. And I'll talk about this in depth later, but I just wanted to raise that as this is kind of where we're going. We're going to be talking about how we do these things at NTIA. But before I transition to that, let me talk to you a little about how these studies are conducted. Sometimes, in the course of trying to determine whether or not you can move off spectrum if you're a federal agency, you might take the lead on certain studies and conduct those studies on the bands in which you operate kind of independently or semi-independently of NTIA. This is what happened, for example, with the Department of War, used to be the Department of Defense, in 2022. So in 2022, DoD conducted a study of the so-called S-band 3.1 to 3.45 gigahertz band as part of something called the Infrastructure Investment and Jobs Act. It's another congressionally designated act, gave the DoD $50 million to conduct a study of their band to see if they can move off those spectrum. I won't talk much about what the results of that was, but that's an example of some of the studies that are conducted that maybe aren't conducted or led by NTIA. Turns out, the short story is DoD determined that it wasn't really possible for them to make that spectrum available. Agencies can either do these kind of feasibility studies alone, separately, or they can work with NTIA to support them. When NTIA conducts these EMC compatibility studies, typically our first goal is to determine if spectrum can be made available, if that's actually practical. It's a plausible thing to do. Ideally, we try to relocate federal systems to new bands so we can reallocate, so take an allocation from a federal allocation to potentially a non-federal allocation, their spectrum or band to exclusive non-federal use. Exclusive means no federal sharing in the band. Exclusively non-federal use. That's typically our first job. In fact, sharing the band is a backup option. Folks may not understand this, but that prioritization of relocating over sharing or clearing over sharing is actually mandated by Congress. So Congress has said, hey, NTIA, if you're going to do a study, we'd like you to move agencies off these frequencies if you can. If you can't, then sharing's your backup option. Process of what we call vacating or clearing a band is usually done through spectral relocation, finding a different place for those systems to operate, or compressing those systems' operations. So you move off a major portion of the spectrum and leave the remaining portion of the spectrum for non-federal use. If clearing is not feasible, based on technical or cost issues, that's when we look into the sharing options. So that's essentially how the prioritization works for these kinds of electromagnetic compatibility studies. Making spectrum available for both federal and non-federal use through sharing typically means we'd have to adjust federal operations and implement technical and procedural ways to share the band. And that's the process by which, sharing occurs. Throughout a study, agencies assess the impact of different use cases. So if you're going to conduct a study, you try to determine, hey, what if we did this with your systems? We moved them to this location, and then we, protected the systems that remain. How's that going to work as a use case? And so an agency would say, okay, well, we'll have to take that back. We'll see what the impact is of our mission based on those particular use cases, and we'll get back to you on it. And that kind of iterative process is how you conduct a study of sharing a spectrum in the federal government. But what's non-negotiable, with this process is that missions and agency missions have to be not impacted. They have to be able to conduct their mission successfully. Can't move off spectrum if you're a federal agency and then, reduce the capability of the agency to conduct their mission. We don't want, weather radars to be able to operate. So you can't get the weather, so planes can't fly, they won't know, what the weather is because we want to make spectrum available. That's not negotiable. So that's the EMC kind of compatibility analysis and feasibility studies that we conducted in TIA. Last thing, the third core element of the Office of Spectrum Management is this idea of strategic planning and policy innovation. America's security, safety, technological leadership, and economic growth depend heavily on sufficient access to spectrum for both federal and non-federal users. It's a critical part of economic growth and security and safety for the U.S. For more than a century, I've talked about the IRAC and other groups within the U.S. have worked to make spectrum resources available for the growing number of spectrum-dependent technologies and services used by both public and private application. OSM focuses on spectrum policy and strategic planning to meet these demands. So today I want to outline how strategic planning can unlock the potential for spectrum access for all and highlight the opportunity for all of you for the research and innovation to play a critical role in unlocking spectrum for all, and kind of in order to meet this growing demand. Strategic planning for ensuring spectrum access calls for a long-term planning process where stakeholders can work together openly, consistently, and transparently while recognizing and addressing national security and economic constraints to meet current and future spectrum requirements for all users. We have to develop a way for everyone to talk to each other. So demands and requirements can be understood and innovation can be brought to the bear to make spectrum available. That is really the key to unlocking it. And as I said, planning is nothing without innovation. We also have to enable innovation efforts to address the needs of both federal and non-federal. In November of 2023 and March of 2024, NTIA published a new national spectrum strategy and implementation plan that identified 4 pillars to modernize spectrum policy, promote innovation, and U.S. leadership in wireless technologies. The Office of Spectrum Management played a central role in developing that strategy and implementation plan. And NTIA continues to develop policy to promote innovation, U.S. leadership, and some of the priorities. Some of the priorities that NTIA is focused on include making vast amounts of spectrum available for full power commercial licensed use, which can be seen in the spectrum auctions requirements in that bill I talked about, the one big beautiful bill. Other priorities include promoting and accelerating space commercialization and supporting the use of AI in spectrum management, all of which I'm going to talk about: space commercialization, the big beautiful bill, all those different things that you may have heard of. Of course, we don't do this in a vacuum. Several advisory groups have been established to provide the NTIA administrator recommendation and input on spectrum issues. There are 2 federal advisory committees that one I've already spoke of, the IRAC, and the other is something called the Interagency Spectrum Advisory Council. And also a non-federal committee known as the Commerce Spectrum Management Advisory Committee, known as the CSMAC. Now, the objective of these committees are to bring to bear additional information to NTIA to help us better understand the demands, the requirements, and innovation that could be brought to bear to enable better management and use of the spectrum. Unfortunately, the CSMAC has, earlier this year was eliminated by the president as a part of an executive order, but that's probably not the end of the CSMAC. We hope that in the maybe months and weeks to come, years to come, it'll be reinstituted. It's very important. It was a way for industry experts to come together on a 2-year basis. So the CSMAC would be introduced and set up for a 2-year cycle. And NTIA would provide them with questions, topics for them to explore, to provide industry expertise to NTIA to help us better manage spectrum. As I said, it was discontinued earlier this year, but the hope is that it will be reinstituted. Of course, finally, the NTIA and FCC have a collaborative relationship. In fact, in 2023, there was an official announcement of spectrum coordination between the FCC and NTIA, and also NTIA renewed what's known as a memorandum of understanding between NTIA and FCC to make clear our coordination and collaborative responsibilities to each other. So let's talk about the one big beautiful bill. I had it up there on the screen for a while. I see you guys have been studying it. As I mentioned, it was passed on July 4th, 2025, actually signed on July 4th, 2025. And the NTIA administrator has made this the key policy initiative for our office. In fact, she recently was quoted as saying, they call it OB3 because One Big Beautiful Bill Act is a lot to continue to say. So I'll say the OB3 is the cornerstone of this administration's spectrum policy. Cornerstone meaning this is what we're going to do as a part of the Trump administration as it relates to spectrum policy. It's designed to push America to the frontier of technology and avoid massive opportunity costs for underutilized frequencies. OB3 requires NTIA to identify 500 megahertz of federal spectrum for reallocation to non-federal use, shared federal use, or a combination of both. That's really much statutory legal language. And what it means is that NTIA has to look at federal spectrum, try to find at least 500 megahertz of spectrum, and transition it to non-federal use. Non-federal use meaning commercial licensed use, or share the band between non-federal and federal use, or some sort of combination of shared and non-shared spectrum. This legislation also requires NTIA to identify at least 200 megahertz by July of 2027. So I talked about earlier this idea of electromagnetic compatibility studies. So these studies have to occur, and we have to complete them within 2 years to identify 200 megahertz of spectrum. That is a tremendous task that we've been put under. As you can see here, the legislation identified those three bands. There's not, even though the legislation identifies these 3 bands, the idea that you would move, you would get 200 megahertz from one of those single bands and move an agency off that entire frequency band, it's not a realistic objective. So in order to identify this 200 megahertz, it comes from a combination of these bands. You might find 75 megahertz here, 75 megahertz there, 50 megahertz here. That's the idea, but that's only for the first 2 years. Then after that, NTIA has to find an additional at least 300 more megahertz of spectrum to meet the law in the next 4 years. Again, this is a tremendous challenge for NTIA and the federal agencies. As I said, NTIA has to collaborate with various agencies to explore and optimize their systems, aiming to find that 200 megahertz. We can say in September, well, it was not September, maybe November of 2025, NTIA hosted what we call our Spectrum Symposium, where our Assistant Secretary talks about spectrum policy. And at that symposium, we announced the first 5 megahertz of spectrum to be identified from 1675 to 1680. So we put this 1% down payment on our 500 megahertz requirement. We're only 99% more to go. But I will say we are underway with these studies. We've begun the study of what we're calling the 7 gigahertz band. It's that 7 gigahertz portion that you see here. And we are in the process of beginning to study the 2700, 2900, and the 4400 to 4940 megahertz bands. So we're on our way with the big, beautiful bill. It's a tremendous challenge. And, the hope is that, we can meet that. Well, it's not a hope. Our Assistant Secretary, Administrator of the NTIA says we will meet that deadline in designating those, that spectrum for non-federal use. But I'd like to move on. Just as we are working diligently to optimize and reallocate terrestrial spectrum to fuel the nation's economy, we're also looking up to the next generation frontier of connectivity in that space. The very same principles of strategic planning, policy innovation, enabling commercial growth are paramount as we unlock the immense potential of the burgeoning commercial space economy. This isn't a separate effort from our terrestrial or One Big Beautiful Bill Act, but it's a continuation of the same national imperative, ensuring the U.S. leads the world in advanced communications. It's clear that we are living in a remarkable new space age, one that is defined by so-called Apollo-style government-led, less by the Apollo-style government-led exploration and more by a vibrant, commercially driven ecosystem. The economic significance of space is rapidly expanding. It's becoming a critical piece of infrastructure for the global economy. You see it everywhere with the LEO mega constellations. It's happening, right? And they're going to need vast amounts of spectrum. Impacting, everything that we do, from logistics, agriculture, to finance, and even public safety. This explosion in commercial space activity is also seen by the WRC 2027 agenda items. More than 80% of the agenda items are about space. It is the next frontier, so we have to be ready. We think of it as kind of an unprecedented opportunity and a clear call to action for NTIA. As the manager of our nation's federal spectrum resources, we have a pivotal role to play. To maintain the U.S. leadership, we must foster an environment that can try to keep up with the speed of innovation. That's why at NTI we're promoting and accelerating commercialization as a core component of our strategic planning and innovation efforts. Our key contribution here is to support what we call streamlining applications for these new and novel space systems. I'll maybe take a slide here. So that when an industry or a company wants to utilize space, they obviously have to have uplink and downlink spectrum to do that. They have to go to the FCC, submit an application to the FCC for use of spectrum. Those applications typically also require federal spectrum. And as I said earlier, FCC and NTIA have a collaborative relationship where we work together to ensure spectrum resources available for all. So an application would come into the FCC, it would identify federal spectrum, and that application would then come to NTIA, and we'd have to work with our interagency partners to identify, what are the constraints, if any, on the use of federal spectrum. That process, from the industry's perspective, takes a significant amount of time. Many, many months, 18, 24 months sometimes for responses to get back to industry about applications. It's just not tenable anymore. So NTIA, the FCC, the White House has said to NTIA, we're going to need to streamline these applications. We're going to have to be very much leaning forward on making spectrum available to all those space companies that we all know about and hear about. The Kuipers, the SpaceX and Starlinks, the Logos, the AST Mobiles, all those companies are critical parts of space infrastructure. And NTIA has a role in ensuring applications are streamlined and we can get back to the FCC about what are the constraints on potential access to spectrum. It's a key part of what we're doing in NTIA. So in order to streamline this process, how do we do it? So our role is to bring all the stakeholders together, all the federal stakeholders together to analyze the coexistence, develop technical frameworks that allow commercial systems to thrive alongside vital national public safety and science-based interests. I was in a meeting yesterday on spectrum, and I heard from a number of experts, radio astronomy, passive sensor experts. They really understand the critical nature of spectrum. They understand what spectrum is very important, why it's important. The idea that the physics allows for different things in different parts of the spectrum, and you can't move those things. And someone asked at this session, how do we get this information out to policymakers? Because they don't understand. And I think one thing that we kind of settled on in that session was you have to be creative as scientists. As radio science, you guys have to be creative. You can publish papers, those are great. Staffers aren't reading papers. Not those papers. Certainly policymakers aren't reading papers. Staffers are on TikTok. Staffers are on YouTube. It would not be unwise for you to try to figure out smart ways to get that information out to those kinds of social media. Staffers here, they talk to their boss, policymakers make decisions. That's just an aside, something to think about. So on that science note, on that side, OSM, we're working with innovators also at the National Science Innovation Center known as SpectrumX. Through collaborations with the National Science Foundation, NTIA, OSM has found ways to explore coexistence research, including radio astronomy and passive sensor research with SpectrumX. This is key to developing innovations in policy. It needs to be backed up by science and research. This will allow us to take advantage of kind of the new space services while also protecting science-based discovery and research. So at OSM, we're taking a kind of leaning in forward approach, trying to ensure that we're working with experts in the field to understand ways to coexist for radio science, radio astronomy, passive sensors, to coexist with what's coming, and that is space-based communications and significantly different new environment. Furthermore, we also firmly committed to working collaboratively and efficiently with the FCC on streamlining these applications and accelerate access to spectrum whenever possible. We do that by providing timely and thorough analysis of federal operations to help ensure the regulatory processes that give commercial space industry the certainty they need in a timely way to invest. So we are kind of balancing act here, right? We have to balance the economic viability of commercializing space with the science-based and discovery responsibilities. And so we need to hear from everybody. And everyone needs to make sure their voice is heard, as they would say. So let's talk more about other, where the space kind of commercialization is going. There are some very prominent and interesting topics I wanted to talk about and get into. I would say nowhere is the promise of space-based commercialization and the space economy more tangible to everybody in this room than the exciting field of direct-to-device technology. Direct-to-device technology, satellite connectivity, has required typically specialized, bulky, expensive equipment. But with so-called D2D promises to shatter that paradigm by connecting with standard equipment, unmodified cell phones directly to satellites in orbit. This is incredible. It's not incremental. It's a fundamental shift that could eliminate mobile dead zones, provide critical lifeline during natural disasters, and connect billions of Internet of Things devices worldwide. And it perfectly illustrates how the commercialization of space will transform our daily lives. So we'll spend a few minutes on this, I think because it's a perfect example of activities and the enormous potential in D2D director. Imagine your cell phone directly connecting with a satellite. No extra hardware, no bulky equipment, just your standard cell phone. And unlike consumer-based satellite broadband services that require dedicated installations, D2D seamlessly works with devices we already have. Some of us who have T-Mobile might have known that T-Mobile and Starlink have a partnership, and you might have D2D already on your phone. So it's feasible due to these direct-to-device technology is feasible due to the advancements in satellite technology, obviously, including the orbit selection, so low Earth orbit mega constellations 500 to 1,000 kilometers above the surface of the Earth. Increasing capabilities of advanced antenna technologies. All these new technologies have brought to bear the advent of so-called direct-to-device. The key, and again, these key technologies includes things like cell towers in space. Essentially, that's what these new satellites are essentially performing like. We work a lot with the folks from ITS. ITS works with SpaceX and Starlink on interesting coexistence challenges. And in fact, our ITS colleagues we're working on collaboration and coexistence with them. And in a meeting, they noted to me that when they looked at the signals that come from the Starlink satellite, they look just like cell phone signals. And they have PCIs, physical cell identifiers, that look as if it's just a tower coming down from satellites, signifying this idea that indeed space companies, D2D companies are building satellites, they just operate, I'm sorry, they're building cell towers, they just operate in space. And that's where we're going. Today, most D2D services use groups of satellites that orbit, again, closer to the Earth, known as the low Earth orbit satellites. These satellites are just a few hundred kilometers to 1,000 kilometers above us. Being closer means, obviously, that the signal doesn't have to travel far, reducing power needs, and making it easier for your cell phone to close that connection. It also means that there's lower latency, which is crucial to things like making voice calls. While it's possible to use higher geostationary satellites 30,000 miles away for D2D, the lower Earth orbits are just better for providing a wide range of high-performing services. Plus, the cost of making and launching satellites has gone down recently, making it more affordable to send lots and lots of satellites in orbit. I'll give you an example. This is all public. SpaceX applied for what's known as a grant to the FCC to use, particular frequencies for their Starlink. Their grant requested 32 gigahertz of spectrum. That's 32,000 megahertz of spectrum. It also requested 29,000 satellites to be put into orbit. That was SpaceX. Amazon Kuiper, all public, requested 7,500 satellites to put into space, and on the order of 15 gigahertz of spectrum. This is all public. You can go to the FCC website. You can go see this. These are the types of systems and the types of capabilities that these companies are looking to, provide with their space applications. So we have to be ready to coexist. We have to be ready to ensure that the science mission continues, but also we have the ability to move forward with these exciting space commercialization. Now, the thing about D2D is it's not, as of now, expected to replace your cellular service. Instead, it's meant to enhance them. D2D is designed to fill in the gaps of coverage. I like to think of it as like three stools of coverage if you think about connectivity. So, we all use our cell phones wherever we go. We all want to be connected. Nobody likes phone calls or drops. Nobody likes to not have access to the internet. And if you think about it, majority of us use our phones indoors. And when we're indoors, the majority, perhaps 95% of folks in here are on Wi-Fi. That's where most of your, data and your coverage lies, is on Wi-Fi. Obviously, when you're mobile and you're outside, you're typically going to be on your cellular network. That's if you have a signal. Now, if you're in a rural part of the country or in Australia, where there's, it's just not technically or financially feasible to have towers everywhere, this is where something like D2D makes a lot of sense, right? And I think generally that's the idea for direct-to-device. If you're looking at a stool of coverage, you have Wi-Fi coverage, cellular coverage, and you have this other idea of kind of non-terrestrial network, D2D kind of coverage. I think it's amazing to think that even though, again, cellular networks cover 95% of the world's population, there's still over 300 million people without access or many more. 300 million without access and then many more with intermittent access. And that's where D2D, again, will fill in and bridge that gap. The dominant and emerging model for direct-to-device spectrum use, particularly in the US, has this name that the FCC, I guess I'll attribute it to the former commissioner, Jessica ROSEMAry. This happened under, when she was the chair of the commission. They instituted something called Supplemental Coverage from Space, or SCS, for direct-to-device. And supplemental coverage from space is just that. It involves partnerships between a satellite operator, SpaceX, AST Global, and a mobile network operator, T-Mobile, AT&T. In this arrangement, the satellite operator is granted permission to use the mobile network operator's license, their spectrum, to provide service from space. So they have a partnership. We're in these locations. You can use my S-band spectrum to provide service through your satellite. That's the so-called supplemental coverage from space. And this path is being pursued by many of the industry most visible players. I've talked about it, SpaceX and Starlink in partnership with T-Mobile, AST Space Mobile with its consortium of partners, including AT&T and Verizon. The primary advantage of the so-called SCS model is its sheer speed to market. Since the SCS model uses the same frequency bands with which standard smartphones are already designed to communicate, this approach requires no modification of your phone. So billions of LTE and 5G handsets already in our pockets can work with direct-to-device. This completely removes the kind of barrier of convincing a consumer to kind of buy a new device for direct-to-device capability. It's a simple business model. Partnership with satellite operator is just another infrastructure provider selling coverage as a service to the mobile network, which then integrates its services to underserved areas and boosts competition in the wireless market. Despite that appeal of the so-called SCS model, there are complications, and it's a complex challenge. The use of spectrum allocated for terrestrial services from a space-based platform is often inconsistent with current international framework established by the ITU. This means that globally, the SCS model operates in kind of a gray area regulatorily. And it requires special country-by-country authorizations, creating a fragmented, uncertain global landscape. So we might do SCS here in the US, might not be internationally the way that folks go. Additionally, there are kind of major interference management issues, technical hurdles if you think about the satellite coverage from space. If you've got a satellite, it's a beam that covers a huge portion of the Earth. Perhaps there are licenses. Maybe T-Mobile has a license in Boulder, and right outside of Boulder, AT&T has a license. What's right outside of Boulder? Broomfield? Maybe right outside of Boulder, Broomfield has a Verizon license. How do you deal with that kind of interference that your satellite coverage might give to the Broomfield? Because there's no license there, and they don't have that connection. So that's a real world kind of intra-network, cross-border complication that the supplemental coverage from space might have to deal with. Maybe not as big a deal now, but as things start to really happen in the direct-to-device world, it will become a challenge that the regulatory industry and the regulatory community and the industrial industry will have to figure that out. So-called cross-border or intra-network or inter-network interference. There is an alternative to the so-called supplemental coverage from space kind of model for providing access. The alternative approach is much simpler regulatorily speaking. It's to use the bands that are already allocated and harmonized globally for what's called mobile satellite service, or so-called MSS. These bands, in which include portions of the L-band and S-band, which I'm sure you're very familiar with, have long been designated for space-to-Earth communications under the ITU. This is the model being used by big operational D2D service from Apple and Globalstar, as well as a strategy for other veteran satellite operators like Iridium and other operations being planned by companies like EchoStar or SpaceX. Just as an aside, some may not know, within the last 2 months, I think it was, EchoStar, which is Dish Network, and Charlie Ergen, they had a deal with Elon Musk and SpaceX to sell their AWS bands of frequencies. So AWS is 1695 to 1710 megahertz, to sell those frequencies to SpaceX for direct-to-device on the order of $8 billion. They sold that spectrum to them. And just recently, SpaceX put in an application to the FCC, like I said, to utilize that spectrum for direct-to-device. So those things are just preludes to what's coming down the pike as it relates to space commercialization and direct-to-device. This model, so that's an aside on EchoStar. The primary advantage of the so-called MSS model is a regulatory clarity and simplicity. This is, since it's already harmonized in the ITU standard, this is probably how globally direct-to-device might be deployed. By operating within these globalized, harmonized bands, this approach avoids the complex national licensing battles that we talked about, the cross-border interference, the disputes that are inherent to the so-called supplemental coverage from space model. The rules are consistent, well-established, and giving satellite operators and their partners full control over their network and the end-user experience. This allows for a predictable, stable path for deploying global service. The historical challenge for the so-called MSS model is obviously the device compatibility. All of our phones don't have those spectrum, don't have antennas in our phones and have access to the spectrum that are the mobile satellite service spectrum, and the chips. So it requires, traditionally required custom designed silicon antennas with the end user devices, thereby limiting the user base and specific hardware. Although the Apple Global Star service, for example, only works with those of you who have those of you who have iPhone 14s, I'm an Android person, can't even say iPhone. But those of you who have the iPhone 14 or newer, your device is already compatible with the so-called Apple and Global Star model. So that's generally what we think about the so-called direct-to-device approach and how NTIA is thinking about it. So let's talk about what the impact will be for 6G as you think about space commercialization and so-called direct-to-device. Currently, your direct-to-device services are kind of basic, if you will. Essentially, you can have basic text and some SOS kind of services. But the long-term vision is for direct-to-device to be natively integrated into the infrastructure of 6G networks. And the 6G paradigm is to use so-called non-terrestrial networks like direct-to-device as a foundational component of a single global unified network. The ambition for 6G extends far beyond obviously delivering faster data rates. The core vision, went a little quickly. The core vision is to create a framework for ubiquitous, intelligent, seamless connectivity that merges physical, digital, and biological worlds. The so-called seamless connectivity is an aside. It dates back to the so-called the three-stool approach that I was talking about with the connectivity. Achieving this vision of the ubiquitous coverage is impossible with terrestrial networks alone. Obviously, you can't put towers everywhere. It's just not technically feasible or financially feasible. For that reason, non-terrestrial networks are considered fundamental native component of 6G architecture from the ground up. In this 6G network, direct-to-device connectivity will play a crucial role, providing essential service connectivity required to enable a host of advanced 6G applications anywhere on the planet. So that includes the so-called immersive extended reality, metaverse experiences, massive scale IoT deployments, smart cities, agricultural, and highly reliable low latency links for autonomous vehicles and drones, and making sure these services don't fail when users are beyond the reach of a terrestrial tower. think D2D will be the architectural element that guarantees the so-called always-on connectivity that these future applications will demand. So that's not where we are today, obviously, with direct-to-device. So the journey for today's D2D services to fully integrated 6G vision will likely occur in distinct phases. And I talked about these space companies requesting many gigahertz, many thousands of megahertz of spectrum, many satellites to put in space. That is the infrastructure that they're building to enable these kinds of ubiquitous connectivity and always-on connectivity for 6G. It's happening now. So we have to, as radio scientists, you guys are gonna have to figure out how are we gonna coexist. Okay, let's talk about the journey though. That takes us from what we talked about, kind of these basic services that we see now with direct-to-device, messaging, one-way location sharing, to this vision of ubiquitous connectivity of services. The key evolution that will be the addition for the new capabilities beyond basic texting. What is that? The roadmap includes the introduction of voice services, basic two-way data connectivity, suitable for rich messaging, simple browsing, dedicated support for massive Internet of Things, and those standards. As you can see here, we're looking at 2026 to 2028 as the ideal time frame for those kinds of services, the commercial voice, rich messaging, narrowband Internet of Things. They're looking at a 2-year window. So if you're designing kind of radiometric equipment, those kinds of things, you have to be thinking about, it is 2026 through 2035 being a time frame where it's a crowded environment for you. And so in the next 5 years following that, in the so-called 2030 to 2035, the goal, this is the goal of the D2D instrument, is to deliver so-called true seamless cellular broadband from space with data rates and performance that get close to terrestrial 4G and eventually 5G. That's what those 32 gigahertz of spectrum are meant to do. Achieving this will be a feat which will require deployment of, second and third generation mega constellations with more advanced and higher capability, even laser-based inter-satellite links for robust so-called space networks. In fact, we are seeing from logos applications for inter-satellite links that allow for this so-called space meshing. So I'm just bringing that to everyone's attention that this is coming, and it's coming sooner than you think. So this will bring me back to my main point, and the one I think that's most important to this audience. In the Office of Spectrum Management, we're thinking about how we ensure space commercial services like direct-to-device can coexist with critically important science-based services from radio astronomy, scientific observations, and passive sensing that have quietly operated in these bands for decades. When I say these bands, I'll talk to you more about what these bands are. The FCC recently issued the Satellite Space Abundance Proposed Rulemaking. This rulemaking looks at expanding the use of spectrum in several high-frequency bands, including 12 to 13 gigahertz, 42 to 45 gigahertz, 45 to 75 gigahertz, and particularly 51.4 to 52.4 gigahertz of spectrum, and the W-band. There's significant interest from satellite and space companies for the spectrum, particularly those with LEO mega constellations like Starlink and Amazon Kuiper. While there are many bands and opportunities for researchers like you to explore ways to facilitate coexistence, I want to highlight the W-band spectrum and the potential challenge of coexistence with these LEO mega constellations. Historically, the W-band has been a quiet frontier for commercial services, and your scientific observations have gone undisturbed. However, the W-band is on the verge of becoming a very noisy domain due to the convergence of two powerful technological trends: the expansion of the so-called LEO mega constellations that we talked about for communication, and the planned use for W-band of WBAN for terrestrial 5G and 6G backhaul, which is the high-capacity links that connect the cell towers to the main network. The fundamental challenge for you lies in detecting your weak noise-like thermal emissions central to Earth science in the presence of these coming high-powered man-made signals that are orders of magnitude stronger than the signals that you're trying to detect. I do want to highlight here, my colleagues at OSM and I are actually presenting a paper at the AMS conference at the end of the month that detail this challenge, the so-called WBAN passive sensor challenge that is coming. But I want to highlight it now for you radio scientists in the room as a potential area for research for all of you. In the coming years, you can expect the deployment of tens of thousands of satellites utilizing V-band and W-band for high-capacity gateway uplinks, user downlinks, and inter-satellite links. These signals from these communication satellites are just fundamentally incompatible, obviously, with passive noise, remote sensing that you guys do. And as you know, these signals are not going to be weak, random thermal noise. They're going to be powerful modulated signals designed for high data rate communication. W-band passive sensor detection of RFI from a LEO satellite is not a single problem but a cascade of interconnected challenges that you guys will face. The physics of the RFI signal, the propagation media, the nature of the sources, and the constraints on platforms all combine to create a uniquely difficult detection environment. The design of future passive microwave radiometers must evolve from assuming a quiet environment to assuming a congested RFI landscape. Perhaps the most fundamental improvement to the current design of passive sensor satellites is moving to filters with much sharper frequency responses or faster roll-offs. Sharper filters allow the sensor to operate much closer to the edge of its allocated band without being contaminated by noise from systems in the adjacent bands, which you can expect. Receiver front ends, especially low noise amplifiers and mixers, must be designed with higher 1 dB compression points and better linearity. For missions that are not limited to size, weight, and power, the so-called SWAP constraints, including potentially a dedicated RFI monitoring system that can, that can be incredibly useful. Instead of relying solely on software within a main processor, a dedicated module, specialized hardware can detect RFI with more speed and accuracy. So if you're trying to detect signals, if you have a monitoring system that's on board, that might be able to tell you, hey, we're seeing interference, so maybe you can avoid that data. It's also the idea of using machine learning to better understand when you're actually seeing data, interference in your data. These are all some ideas of ways for you to make your sensors more robust, ensure that your discoveries and observations can coexist in the coming environment. So with that, I'll conclude here. I'll say thank you to Jay Messina, thank you to the National Committee for inviting me here. Hopefully you're as excited about the opportunities ahead of us for space commercialization and coexistence and the technical studies that will be conducted for unlocking spectrum access for all users. I hope I've been able to provide you with some insight into what we do at OSM, spectrum management and research, and policies that are at the forefront of innovation and critical to economic growth and security of the nation. There are so many exciting opportunities for you engineers and radio scientists in the room for you to play a pivotal role in our nation's advancement. Thank you very much for your time.
And we have a few minutes for questions. Please use the microphone.
Hi, Eric.
Hi, Paul. Could you comment on the impact of the sale of the 1695 to 1710 for the 17 NOAA ground stations? They already have an RFIMS system, but if they're going to get, but the satellite only passes in 10 minutes. Is there going to be an accommodation for that?
It's a great question, Eric. And we are hearing from NOAA, what does this mean for us? So a little background. 1695 to 1710 is part of the spectrum that NOAA uses for polar orbiting environmental satellites, so-called POLE satellites. They provide kind of weather information to the country. And then as a part of the so-called AWS-3 auction, that spectrum was sold off for terrestrial use. And in order to share the spectrum with the terrestrial providers, NOAA identified, let's call it 17 sites where they said, hey, at these particular locations, we need protection. So if you're going to put a tower, a terrestrial tower in these locations, we're going to have to coordinate to make sure you're not going to cause us interference at just those sites. Other than that, hey, Dish Network, you can put your system, your towers out anywhere and provide, service to, the public. That was 2017, maybe 2018, something like that. And so it's now 2026, so 8 years from now. So it's been 8 years. There have been very few towers that Dish Network has put out. They've done very little build out of an actual network. And something like 3 or 4 months ago, EchoStar decided, hey, we're going to sell our spectrum to SpaceX. And SpaceX, bought the spectrum a couple months ago, and within a month, 2 months, they put out an application to the FCC saying, hey, we're going to use this for direct-to-device immediately. And, you can imagine if you're NOAA, you're like, whoa, what's happening here? And the impact of that sale on NOAA is, how are we going to protect our systems? How are we going to protect our sites? What does protection for our sites look like? And, to your point, Eric, we're going to have to figure that out. As you can imagine, you've got a cell tower in space. It is downlinking to, we don't know yet, maybe user terminals, it's unclear. But if it's downlinking to user terminal, signal's not going to be as strong as a terrestrial signal that is there, but it's going to have an impact perhaps on those 17 sites. So as a part of what we do at OSM, working with the interagency, our colleagues at NOAA, we're going to have to try to figure out how do we mitigate that impact. Do I know exactly what that's going to be right now? Yes, obviously I do. I just don't want to tell you guys. No, I'm just joking. No, we have to figure that out. It's a great question, though.
More questions? Go ahead.
I might.
Okay. Thank you, Dr. Ransom. So question following big sell-offs of spectrum and, allocations that may take a long time or last for a long time, big grabs for spectrum, as you mentioned in some of the FCC filings. So what are the prospects that you might see for more of a market that actually operates at shorter timescales and sizes?
It's an excellent question. So if we think about the way that kind of space users use or request and get access to spectrum, it's kind of on a first come, first served basis. It's a processing round thing. So if you're the first one to market or you're the first one to get to grant the access to the spectrum, then you have priority perhaps, and folks that come after you can get access to the band, but then they can't interfere, so they have to access the band on a non-interference basis, essentially. But there's another part of the question that I think is interesting. Something that we're thinking about is, E-band's a very important part of the spectrum for, sensing and radio and passive sensing. So it's like 86 gigahertz to 92 gigahertz, very important part. On both sides of that part of the band, the W-band side, the upper portion side, 92 and up, and 86 and below, you're going to have perhaps, space communication satellite signals. And while they're adjacent, we all know that there's out-of-band emissions that happen, and those will impact the frequencies that are the E-band frequencies, right? And the more signals you have adjacent, the higher the out-of-band emissions and the higher the floor gets. How do you determine, when you're at capacity, right, and those out-of-band emissions, where it's going to really impact the E-band sensing? One, you need to determine what that is, right? Then you're going to have all these companies coming in wanting to use this spectrum. How do they determine, when, you can no longer put any more ground stations up, right? Because if you're going to be, let's say you're going to be uplinking in that band, and you're going to need ground stations, and you got lots of power, you got to uplink. How many of that? And how do you determine who gets the most number of ground stations? Does SpaceX get 200 and Kuiper gets 50? How do you determine that? So it's a challenge to figure out. It's a policy challenge. How are we going to work that out? And, we got lots of work to do in our little agency about trying to figure out and find solutions to those challenges.
Thank you.